This is Knowing the Universe, History and Philosophy of Astronomy, and I am Chris Impey, Distinguished Professor of Astronomy at the University of Arizona. In this module, we'll be talking about atoms and stars and telling their story. We start with the Sun, our star. There was a big debate playing out in the 19th century over what powered the stars, and in particular the Sun. The main protagonists were William Thomson, Lord Kelvin, who was a mathematician, physicist, and later engineer. He was the preeminent name in physics in the late 19th century, the founder of the field of thermodynamics. He calculated, based on the known energy source of the time, chemical energy, that the Sun could only last a few thousand years. That was even too short for Bishop Ussher, who was counting the begats in the Bible. And that, of course, was true of any form of chemical energy. The idea that the Sun was made of coal or gas or oil is kind of ludicrous to us now, but nobody knew about nuclear power at the time. He also then estimated that gravitational contraction could extend that lifetime, but the longest timescale he could get was 100 million years or so. And that was long for him, but too short for Charles Darwin and Charles Lyell. So both the geology and the biology of the time needed hundreds of millions of years to play out for what we saw in the fossil record of the Earth to be true. Kelvin insisted these times were too long, and so it was a crisis. Really, it was a crisis in physics because new physics was needed, and that, of course, was eventually found from the source of nuclear fusion. We think of the Sun as a nuclear device, but it's nothing like a bomb. It's actually exquisitely balanced and stable. It's in what's called hydrostatic equilibrium, where at every point within the Sun's volume, there is a balance between the pressure outwards from nuclear reactions, fusion, and gravity inwards. And so the Sun is actually stable. If there was an outward push to make the Sun smaller for some reason, the temperature would go up, the nuclear reactions would increase, and it would be a push back. If the Sun for some reason got less dense and larger, the temperature would go down, and the nuclear fusion rate would go down, and the pressure would decrease, causing the Sun to shrink again. So in fact, the Sun is exquisitely balanced and completely stable, and it will be stable for billions of years to come. Here's the solar dynamo. This is the mechanism that was understood in the mid-20th century by which the Sun's magnetic field gradually twists and the Sun's magnetic field chaotically dissipates and then reverses on a time scale equal to the solar cycle. This is what causes the solar cycle. It has an effect on the Earth's climate as well. And it happens because the Sun is rotating differentially, faster at the equator than at the poles. Here's the mechanism near the surface of sunspots, where magnetic field lines loop out of the Sun, out of its photosphere, pushed upwards by upwelling energy from the fusion reaction's interior. And you can see where the field line penetrates the apparent visible surface, you'll have a pair of slightly cooler regions where energy is escaping. Sunspots are slightly cooler than the surrounding regions of the Sun's surface, and energy can also escape from those magnetic field lines. So we always see sunspots in pairs, and they are the telltale of the solar cycle, which really speaks to the gradual buildup and then destruction of the magnetic field inside. The Sun is dynamic. Here's animations taken from a solar satellite of the previous decade, SOHO, showing spectacular flares and prominences. This loop of hot plasma pushing off into space is 5 times the Earth's diameter as it loops out. Incredible solar storms that push energy into space and actually affect the Earth's weather and telecommunications. You see here, even compared to the size of the Sun, 1 million kilometers across, these are enormous storms and filaments. And so the Sun's energy source was hotly debated. Stars are gravity engines. The pressure of gravity in a star's core raises the temperature to millions of degrees, and that is hot enough that atomic nuclei move fast enough to overcome their nuclear repulsion from the electrical force. Remember that the Sun is primarily composed of hydrogen and helium, and hydrogen is simply protons and electrons. So it's those protons moving very fast with positive charges that resist coming into contact because of the electrical repulsion. Eventually, if the temperature is hot enough, they actually stick in a process called nuclear fusion. Fusion is millions of times more efficient than chemical energy, So the sun's lifetime with this mechanism finally becomes consistent with the long age of the Earth demanded by both geology and biology. And this mechanism is really the conversion of mass into energy, into sunlight. In fusion, as we see from the scales on the lower right, the product, helium nucleus, 2 protons and 2 neutrons bound together, is slightly lighter than the sum of the nuclei, 4 protons, that went into the reaction. And the mass difference is converted into energy that makes its way out of the star. It's this binding energy released into sunlight by a very efficient process where you take the mass difference and multiply by c², a large number, that gives the phenomenal energy of the sun. But the real mechanism actually involves the mechanism of quantum tunneling, as we'll see here.
Did you know that if the sun were fueled by combustion of, say, gasoline or wood, it would burn out in just a few millennia? So how is it still here after 4.5 billion years? Physics. The sun is like a big nuclear submarine. In the sky. That's right, it's fueled by nuclear reactions that fuse hydrogen atoms together into helium and other heavier elements, releasing huge amounts of energy in the process. In this way, the sun is slowly converting its mass into energy, in the form of sunlight, and it has more than enough fuel to last billions of years. But nuclear fusion's no walk in the park. On Earth, we need to heat hydrogen up 100 times hotter than the sun to get a fusion reaction. So how does the sun do it? Quantum tunneling. There's a small chance, which I'll explain later, that hydrogen atoms, even if they aren't quite hot enough for fusion, will fuse together anyway. And the sun is so big and has so much hydrogen that these small chances happen all the time. And that's what keeps the sun energized. So when the sun shines tomorrow, give thanks to quantum mechanics.
So understanding why the sun shines actually could not happen until we had the quantum theory early in the 20th century. Also until we understood the mechanism of the atomic nucleus.
The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees. The sun is hot, the sun is not a place where we could live. But here on Earth there'd be no life without the light it gives. We need its light, we need its heat, the sunlight that we see. The sunlight comes from our own sun's atomic energy. The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees. The sun is hot.
The sun is so hot that everything on it is a gas. Aluminum, copper, iron, and many others.
The sun is large.
If the sun were hollow, 1 million Earths would fit inside. And yet, it is only a middle-sized star.
The sun is far away.
About 93 million miles away. And that's why it looks so small.
But even when it's out of sight, the sun shines night and day. The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees.
And that's the end of this topic.